In this demonstration video, we'll be discussing Nucleus ReadyStart in the context of software trace and analysis. Nucleus ReadyStart is a bundled product package. It consists of host-side development tools and runtime software. Nucleus ReadyStart's trace and analysis capabilities are powered by Mentor Embedded Sourcey Analyzer. My name is Arvind Raghuraman, and I'm the kernel group lead in the Nucleus engineering organization. Here is a brief agenda for this session. We're going to start with an introduction to the Nucleus software trace solution. We'll be looking at some high-level implementation details and some usage models. And then we'll move on to the demonstration platform. The demonstration platform that's going to be used for this video is Stella, the balancing robot. We'll be discussing the internals of the robot, and then we'll be seeing how trace data is captured on the system. We will then move on to a hands-on demonstration session, during which we will do a live data capture on Stella while it's balancing, and then we will use Mentor Embedded Sourcey Analyzer to gain some very interesting insights into software runtime. This is a high-level overview of the Nucleus software trace system. The solution comprises of host side and target side components. On the host side, the user is provided a cohesive infrastructure for configuration, acquisition, and visualization of trace data, all within a unified workflow. And on the target side, we've added a new service to the Nucleus operating system called the trace service. The trace service provides the application API infrastructure required for application instrumentation, trace data communications between target and host, and some APIs for arming and disarming trace instrumentation that's present in the kernel side and on the application side. The Nucleus kernel has been pre-instrumented by us for capturing events of interest during kernel runtime. So obviously, without any explicit instrumentation by the application developer, on the click of a button, we have kernel runtime information available to us, as long as kernel tracing is enabled during build time. If the kernel tracing option is not enabled during build time, the instrumentation has no impact on kernel runtime. We support multiple methods for trace data communication between target and host. The user can choose to consume data during target runtime using one of the trace communication APIs provided by the trace service. Obviously, this method attempts at making more trace buffer space available for data logging, but it has impact on the CPU overhead, right? We'll be expending CPU resources during runtime to transmit trace data from target to host. The solution also offers an alternative method to consume data post runtime over the debug interface. It could be JTAG or the Nucleus debug agent. In this model, the users are able to download software over JTAG to the target, run code for the observation interval that's under investigation, and then halt the system and then consume data offline over JTAG, and thereby not incur any CPU overhead towards trace data communications. Moving on, I'm going to take some time to talk about our demonstration platform, which is Stella, the self-balancing robot. The picture here in the top left corner shows the robot and its remote controller. And as you see, it's a two-wheeled robot that's basically able to balance itself in upright position. The robot and the remote controller have Zigbee connectivity that enables for wireless remote control. And the remote controller provides LCD touch panel based user interface, which serves as a joystick using which the demonstrator could basically drive the robot around and showcase its operation. Both the robot and the remote controller were developed on Nucleus RTOS. I have a short video clip here that showcases the robot in action. And while this is going on, I'm going to take the time to talk about some internals of the robot's construction and also its control loop and some details regarding it. So this is a pictorial representation of the sensors and actuators that are used on the system. We use a MEMS gyroscope that is used to measure the angular rate of fall about the vertical, and we basically have servo motors that enable us to provide our actuation signal that would cause the robot to move backward and forward, trying to compensate for the tilt incurred due to its natural propensity to fall down about its axis. So these are servo motors. Since they are servo motors, they come with quadrature encoders coupled with the shaft. So these encoders could be used for measurement of the wheel position, which is what it's configured for. And yeah, that's pretty much it. It's worthwhile to note the notations we've used here. So psi is the tilt angle and theta is the wheel position. We'll be using this notation later during the demo. This is the embedded control loop that basically enables for balance control on Stella. This part is the embedded controller that's implemented as a Nucleus thread that runs on software on the processor. And this is Stella itself, the robot plant. So the measured variables from the system are the tilt angular rate, which is measured by the gyroscope, as I mentioned, and the left and right wheel positions, which are measured from the quadrature encoders that are coupled with the motor shaft. So this comes as an analog voltage output from the sensor, and this is basically a quadrature output that comes from the motors, from the encoders on the motors. These inputs are sampled by software, and we do some derived processing to derive some parameters. The tilt angular rate is basically integrated over time to get the tilt angle, and the wheel position is differentiated over time to get the wheel rate. So these four variables constitute our state vector, which basically is fed into a controller, which is a proportional integral controller, as you see here. There is a reference vector that comes in, so the error signal that's generated is basically used as input to the controller, and the controller takes the control action, which is fed to the motors in the form of a pulse width modulated signal that goes back into the Stella plant, as you see here. We used formal design methodologies to develop the system. So we did initial system modeling, open loop and closed loop analysis, and controller design in MATLAB, and then we moved on to the embedded deployment, and then we went through the tuning phase to get the robot to balance in an upright position. This is a high-level overview of the hardware and software components that were used for development of the self-balancing robot. So as you see here, both the robot and the remote controller use a TI Stellaris-based platform. It's a Cortex M3 based part, and then we used a Zigbee daughter card that enabled for wireless connectivity. On the software side, we used Nucleus RTOS and we used TI Z-Stack to enable for Zigbee wireless interface. And we have the robot and the remote controller application running on top of the stacks, respectively. We used Mentor Embedded host-side development tools for the development of this demo. This slide shows how software trace data is captured on the target side and handed over to the host side for data visualization and analysis. As seen here, this is a robot, and this is the software stack running on hardware. The software stack comprises of the operating system, the middleware, and then the robot application itself running on top of it. The operating system's kernel pre-instrumentation has been enabled to capture kernel runtime, right? And the application has been instrumented to capture various variables of interest during runtime. So the application data, the application trace data, and the kernel trace data are logged onto onboard memory buffers that are present in the system. We have an 8 megabyte external RAM module that we've attached to the system just to enable for trace data logging. And we'll be using a post-runtime data consumption model to fetch data from the target to host, which basically means that we'd first load software to the robot. We'll let it balance for a while, during which trace data is going to be acquired and logged onto the onboard buffers. And we would halt the system after that. And once the system is halted, on the click of a button, we will basically fetch all of trace data that's been acquired on onboard memory buffers to the host side over JTAG. And the data will be available for visualization and analysis. Another important point to mention here is that the Mentor Embedded Sourcery Analyzer is really an open-ended platform that enables users to import any type of data into its database and perform visualization and analysis of the data. It is not tied to Nucleus software runtime in any way. So yeah, we could possibly envision a system where data comes in to the host side from external sources as well. So for example, if we have some kind of external data acquisition device that is capable of measuring real-world variables such as analog voltages, current, etc., etc., we can put together a system where one would be able to visualize software runtime and the real-world variables all within a unified time frame, as long as we have mechanisms in place to synchronize the time bases between the embedded target and the external data acquisition device. Having said that, let's move on to a hands-on demonstration in which we'll be tracing and analyzing the balancing robot's software runtime. Let's get started with the demonstration. This is Nucleus ReadyStart, and what we see here in the Project Explorer pane is the application project, the balance board application project, and the system project, which consists of the operating system and the board support package that consists of the drivers and all the good stuff. Let's quickly see how trace is enabled on the target side. The Nucleus ReadyStart provides for a UI-based system configuration tool, and this is it. I can just expand on the OS node, the services node within OS, and enable the trace component. The trace core subcomponent basically provides for all the build time options that are available for trace related configuration. So here we specify the trace buffer size, whether kernel trace support is turned on or off, whether kernel boot time tracing is turned on or off, and things like that. So we've enabled kernel trace for this particular demonstration. Let's quickly look at the application. As I mentioned earlier, the balance board application has been instrumented to capture various elements of interest during software runtime. So here is a trace marker that captures a string payload. So we have a human readable qualifier and a string payload that is captured at this point. And similarly, we capture all logical application transitions during runtime. And if you look at the balance control task, we would be capturing various variables of interest. Here we captured I/O variables, and within the controller function we capture all the system states, the proportional integral and integral control efforts, and so on and so forth. Basically, this is how we would typically instrument an application to capture various elements of interest. We also have an open-ended marker which takes in a printf-like format specifier, using which the user can log composite payloads with a single call to a new trace mark. So let's move on to the demo. What I'm going to do now is I'm going to connect to the target and download code, let the robot balance for a while, run code, let the robot balance for a while. While the robot balances, trace data will be collected on chip memory, and then we're going to halt the system, consume the data over JTAG, and visualize it. So this is a video stream from my desktop. What I'm going to do is I'm going to launch a debug session. So debug as a Nucleus application. So this is the debugger tab where all the default options should work for me. I switch to the profiler tab, make sure profiling is enabled, and I've chosen debug interface as my trace communication method. And here, this is the Stella target, and I'm connected to it over a USB cable. So this particular target provides JTAG in the form of ICD over USB, in-circuit debugging over USB. So just with this cable, I'm able to do a JTAG based debug session on this particular target. I'm turning on the board. I'm going to put the robot flat, and I'm going to start the debug launch. Yes. And we are connected to the target. So what I'm going to do now is I'm going to run the application. The application's running. So I press this little button here that kickstarts the application. Calibration is done. It's asking me to hold the robot standing. There we go. So the robot standing. We can push it around a little bit. So I'm going to hold it and halt the system. So now the CPU is halted. I'm going to put the robot back on my table, and I'm going to click on this little blue button here that says Visualize Trace. So on the click of this button, what's going to happen is we're going to fetch all of trace data that was collected on the target side over JTAG, and we're going to switch perspectives within the IDE to the Mentor Embedded Sourcey Analyzer perspective, and we'll have data presented to us that is ready for analysis. So I think we're done with the video stream, so I'm going to close that. Let's click on Visualize Trace. What's happening now is we are acquiring trace data from the target over JTAG. So the data acquisition was completed from the target, and basically this is the default visualization that's rendered within the Mentor Embedded Sourcey Analyzer perspective. So what you're seeing now is the Nucleus execution profile, which is a high-level overview of the kernel runtime for the period it was run. So you see the CPU state, all the high-level interrupt service routines that are present in the system, the low-level interrupt service routines that are present in the system, all the task instantiations that are present in the system. So these two are kernel system-specific tasks that were used during boot time, and they finished what they were supposed to do, and one suspended, and the other is auto clean task, which deleted itself. So as you see, we can basically expand upon any point of interest and get more detail on what was actually going on at that point in time. We also have this feature where we can select this tooltip functionality and hover over any state of interest and get more in-depth information on what actually happened at that point in time. So I'm right now hovering over a Hisser creation event, and we have the Hisser control block address, the entry function, the stack pointer size, the Hisser name, the status, and so on and so forth, right? And similarly for tasks, whatever is relevant in a given state context, you would see more information on that particular state. So let's zoom out. Let's see how I can make some temporal measurements on software runtime. So for example, let's measure the interrupt latency on the system. So I'm going to expand upon a period of interest. So we see that the CPU was idle, an interrupt fired, and then we transitioned from being idle to being busy, right? And then here we have the low-level interrupt service routine status, which was in stop state. The ISR started running at this point, and then it completed execution at this point, right? And I want to measure the time it took from the point the interrupt fired to the point the ISR started executing. So I can select a waveform and drop these markers that are available to me and latch them to logical state transitions to measure delta time that transpired between those state transitions. So I just dropped two of those markers, and the delta time between these two events is 4.5 microseconds. So that is the interrupt latency for this particular system, which is running at 80 megahertz. With that brief introduction to kernel visualization and analysis, let's now move on to application trace data visualization and analysis. So I can pretty much view any of the application variables that were traced using the agents available under the filter palette here. So I'm going to use this wizard to basically pick the event type that I would like to visualize. So these Nucleus Plus event types are the kernel runtime events that were logged. We have these pre-canned agents that enable for visualization and analysis of that data. But what's important to note here is that along with the kernel runtime event types, we also see some application-specific event types that we instrumented and logged in the application space, right? If you remember, I had a trace marker that was logging a string payload and the human-readable qualifier that was used for the string payload was app status, which is the application status. So let's say I want to visualize the application status. So I pick that and I want to visualize it as a state waveform. So I pick the state waveform and I say OK. And here is the app status trace visualization. So we were capturing various logical transitions in the application runtime, right? So if you see here, this is when system initialization began, and then we were waiting for the user to press the button, and then when the button was pressed, we spent about a second doing gyro calibration. It's 5 to 6 seconds, and then the application is designed to give the user 5 seconds to hold the robot up standing. So that's right here, from 6 to 11 seconds, and then the balance control kicks in. You see that the balance control task has become active now. It executes at the rate of 200 Hertz, and this is the display task, which runs at 10 Hertz. I'm sorry, 2 Hertz to enable for update of display that's present on the robot. So that's the application status. Now let's try to look at one of the variables that was logged. So if you remember, there were a number of trace instrumentation markers in the application that were logging the float data types, which were internal variables in the application, right? So I'm going to try to look at the gyroscope data that was acquired. So I used gyro raw as the qualifier for the raw gyro value that was acquired as a float variable. So I'm going to pick that. I want to visualize that as an analog waveform. So I say OK now, and here we are. So let's expand upon this period of interest. And this basically was the raw gyro count data that was acquired during runtime. And now I can basically visualize the same data in a tabular view as well. So the trace viewer that's available to me here gives me a tabular representation of all the trace logs that were acquired, ordered in the sequence of timestamps. I can basically filter what's available for visualization here by selecting any of those event types, and there's a lot of filtering capability provided through this wizard, but I'm not going to get into that right now. I'm going to move that parallel. Well, let's pull it down. So we are now looking at a tabular view of trace data that was logged along with the graphical representation as well, and we have a region of interest that we want to focus upon. Right now, I can choose this selection marker, and I can select this waveform. And if you notice, as I latch the selection marker to the consecutive raw gyro count value that was acquired, you see that the table here gets updated to that particular trace log where the selection marker is placed. So using this feature, we can basically traverse application logs or kernel runtime logs and be able to make cross correlation with this tabular data that's present here to make sense of what happened before and after easily. Right? Let's get rid of that. And now I'm going to add, so we get the raw gyro count and then we do a bunch of signal processing on it, right? So we do, so there is a filter that captures the offset drift. So we basically subtract the gyro offset from the raw value, and then we scale the gyro offset, we scale the raw value to provide us angular rate of fall in degrees per second. So that's all the conversions that happen. So I'm logging the gyro input data path at all of those stages. So I'm going to add the offset compensated profile that was logged, and I can also add the scale factor scaled profile that was logged. Gyro data was the ready to use gyro value in degrees per second after the signal processing. So we have all of these profiles here. Again, everything presented within a unified time reference along with kernel runtime as well. I can also drag and drop these waveforms on top of each other and give them and differentiate them by giving them unique colors. To better understand what went on during the signal processing, during software signal processing. So what we are looking at here is this profile is the raw gyro count that was acquired. This profile is basically the offset compensated profile, and this green profile here is the offset compensated profile scaled to provide us angular rate in the units of degrees per second. Let's say I want to make sure whether the signal processing is occurring accurately. The Mentor Embedded Sourcery Analyzer provides some really useful tools to perform mathematical computations or other scientific computations on waveforms, data available in the form of waveforms, and generate derived waveforms. We also have a measurement tool that allows us for measuring various interesting parameters about a waveform. We'll look at how it will be used and the various interesting visualizations that we can deduct using this tool right now. So what I'm going to do is I'm going to use my calculator tool to basically perform the signal processing activities that occur on the raw gyro count value and generate a waveform and see how that compares with the software computed waveform. I'm going to now add the offset compensated, the gyro offset drift, which is also captured using software trace markers. We're going to need that to be able to do the post-processing. So this is the offset drift that was captured in software, and I'm going to use my calculator tool to do the math to confirm my gyro data derived waveform. So I select the raw gyro waveform, and then I know that I can subtract the offset drift from the raw count to generate the offset compensated waveform, and then I can basically do my scale factor math to make sure that the final computed gyro data is accurate. The ADC input span is 1024, and my gyro measurement span is 200 degrees per second. And that is what I need to do to scale it, the raw gyro count value to degrees per second. So I can just say, oh, I need another parenthesis. So this is basically a formal expression on a waveform. I'm not just subtracting waveforms here, I'm also doing some additional arithmetic on the subtracted waveform. So let's generate that waveform. Let's see invalid syntax. Okay, I think that should do it. There we go. So this is our computed gyro data in degrees per second, right? I'm going to compare that with the software calculated gyro data, and we see that it's on the dot. The waveform superimpose perfectly, which means that our software computation is accurate. So let's move it back here. So this is not the only thing that we can do with the calculator tool. If you see the functionality that's available to you here, we have a pretty diverse set of mathematical operations that we can perform on trace data that's available. So you've got this trigonometric palette, which provides you all trigonometric functions that can be applied on trace data sets. If you are able to log a complex array of trace data, an example could be a time domain frequency sweep that's being done in software to assess the closed loop slip stability of a system. So in such scenarios, we could pretty much generate Bode plots and measure the gain and phase margins of complex using these complex functions provided here. We have a statistical palette which allows for generation of histograms. We have fast Fourier transforms, inverse fast Fourier transforms, and various transformation functions available to us as well. We have a logical palette. This basically enables you to extract data from the core data set, and we can also assign custom mathematical expressions which can be invoked using these shortcut functions. So yeah, this calculator tool basically gives you a wide array of mathematical computational capability that can be applied on the core trace data set that was acquired. Let me show another example. I'm going to use the statistical palette and generate a histogram to try to determine how much energy I'm spending towards balance control on the robot, right? So one of the items I'm logging is the motor's PWM the pulse width output that I'm giving to the motors. So I'm just going to visualize one of the pulse width output that was given to the left motor over time. And you see this is the profile. Since it's a pulse width output, you see it spans between 0 and 100, right? It's percent output. So what we're going to do is we're going to find the frequency distribution of the pulse widths produced at various parts of the span to try and assess within the pulse width actuation span at what pulse width percent I'm operating most of the time. So I'm going to again pull this calculator tool. I'm going to import that waveform, and I want to generate a histogram this time. I want to have 10 bins to generate my frequency distribution of pulse widths produced on the actuation side. So I say OK, and then I say enter. And what you see here is a histogram. So we see that we're for about close to 1,000 samples of the actuation output was generated within the 0% output pulse width, and the next highest is around -20%, and the third is around +20%. And we spend very less time at higher pulse width, so we'd obviously be consuming more energy at higher pulse width percents than at the lower pulse width percent. So the system seems to be operating satisfactorily, but it can obviously be improved. But the point I'm trying to make here is that this calculator tool, it's that easy to basically generate such interesting deductions based on a core data set using the various arithmetic functions that are available to you in this tool. I'm going to now delete these waveforms, and basically let's move on to a different topic. which is the usage of the measurement tool that I mentioned earlier. So we're back to the kernel runtime profile and the application status profile. I'm going to once again add the raw gyro data value to illustrate how the measurement tool can be used. So let's pick that. So that's been added. Again, expand upon the region of interest. And now I can select this waveform and start my measurement tool. And let's say, so if you see this measurement tool, there are various aspects of a waveform that we can measure. So we can measure frequency aspects. There is a general category under which you can basically do level crossing, slope, waveform crossing, where you can import two different waveforms and detect when one waveform crosses over the reference waveform, which can be pretty interesting in a lot of use cases. And there's a level category where you have various aspects of a waveform that are measurable. So the amplitude, average, baseline, minimum, maximum, AC coupled RMS, peak to peak, anything that makes sense that you want to measure on a periodic signal, right? And there is a statistical option as well, and you also have a time palette where you can introduce delays into waveforms that have been measured and do interesting things with it. But yes, as an example, what I'm going to do now is I'm going to use some features in the general palette. So I'm going to import my gyro data, and I want to detect level crossing, and I want to detect every time my angular rate crossed say 450 raw gyro counts, right? We want to apply that to the visible region of X only, and I say apply. So if you see here, basically it displays this line, and if I right click and if I look at the measurement results, it pretty much gives me every timestamp during which the level crossing occurred, and I can basically pick what I'm interested in and see that update in the graphical view, and make more and take a closer look at what happened and why it happened, right? Obviously we have contextual data available to us, so if we are interested in this particular data point, we'll expand upon that, and then we'll see what actually happened in relevance to what else was happening in the system. So that is a useful feature. And similarly, we can also the measurement palette can be used to measure other waveform specific parameters like amplitude, average, baseline, maximum, minimum, peak to peak, exit maximum, exit minimum, visible region of X. You say apply, and within a click of a button you have all that information presented to you. Yep, it's very easy to interact with and cross correlate with other object transitions to make sense of why a particular event happened, and gain more insight and in-depth understanding of what went on. So let's get rid of that. Now I'm going to talk to you about an application problem that I encountered while I was using the Mentor Embedded Sourcery Analyzer to trace Stella. So what I'm going to do now is I'm going to add visualizations to visualize the left wheel angle that was acquired, and the right wheel angle that was acquired. Give them different colors. And I'm going to superimpose them. You see that we have a bias between the left and the right wheel angle, which means that this is going to cause the robot to turn about its z-axis just a bit as it is trying to balance. And I wonder why. So let me look at the PWM signals that were given to the left and right motors, right? So I'm going to look at the PWM left software variable that was traced, and PWM right software variable that was traced. give them a different color so we can differentiate it. And I'm going to superimpose that. And now you see that the left and right PWM signals that were given to the corresponding left and right motors, they're pretty much identical. These waveforms superimposed, but for some reason there seems to be a bias that's persistent for the entire course of the runtime, and which seems to be getting worse over time. And I want to, although I don't understand why this is happening, I want to try to capture or characterize how this trend is creeping over time, right? So now I can pull in my friend, the calculator tool, and I'm going to pull in the left gyro waveform. I'm going to subtract the right gyro. Sorry, let me clear that. So I'm going to pull in the the left wheel angle waveform, and I'm going to subtract the right wheel angle waveform from it, and basically generate a profile of the bias and how it is drifting over time. So I'm going to label this as my wheel angle bias drift. And now let's say I want to try to fit a line to this. So again, I have my measurement tool, using which I can use the statistical measurement palette, import my waveform, and I want to see the best fit. And there we go. I've got my slope and my coefficient. So it is really that easy. Imagine having to do this this kind of characterization in a traditional environment. We're going to have to switch between a modeling tool like MATLAB, and we're going to have to somehow get software trace data and be able to visualize it, visualize and analyze it in a way that's comparable to what we're doing now, and then switch back and forth to try and characterize various application-specific anomalies that are happening during runtime. But this is really the value of the Mentor Embedded Sourcery Analyzer. With a few clicks of the button, you can deduce various interesting aspects of software runtime and the application as well. Moving on, I'm going to now switch over to a previous trace data acquisition that I've done, just to show a high-level overview of all the various data visualizations that can be done for this particular application. So this is the visualization. So we're looking at the CPU state. Here is the CPU utilization profile, and then these are the various tasks and interrupts and high-level interrupt service routines present in the system. These are the system states, that is psi, psi dot, theta, and theta dot, which is the angular rate, the tilt angular rate, wheel position, and wheel rate. This is the gyro input, the gyro drift, calculated gyro data, and this is interesting, right? Here we are looking at a superimposition of various aspects of the control action that were taken to compute the total control output. So this is the control effort that's proportional to the tilt angle, the control effort proportional to the tilt angular rate, similarly effort proportional to wheel position and wheel rate. So just by looking at this and analyzing it, we can easily understand how each of these control efforts contribute towards the total control action, which is total proportional control action, which is shown here in this green profile. And then we have the integral control action in this blue profile, and the sum of these two basically provides the total control action. So this kind of gives you an idea of the kind of understanding that you would get by just superimposing various variables and analyzing them to understand various aspects of your application. So I'm going to switch back to our current trace visualization, and now let's look at some application aspects of this demonstration. So as I mentioned earlier, we got a balance control task which runs at 200 Hertz. and then we have a display task which runs at 2 Hertz, right? So I want this balance control task to consistently run at 200 Hertz, which means that this is the hard deadline in the system. It's a real-time system, and this is the hard deadline in the system. If I'm unable to maintain this 200 Hertz control loop frequency, my quality of control is going to deteriorate, and since Stella is an inherently unstable system, the robot is just going to fall on its face. So to try to understand the quality of service this particular task provides for the control action, I'm going to try to measure the jitter and its frequency. So again, I'm going to select the task. I'm going to select my calculator tool, import that waveform, and I'm going to generate a waveform that would be high every time my balance control task is in the running state. Right. So if you see here, this basically generates, let's give it a meaningful name, balance control activity. And if you expand this, you would see that it's basically a square waveform, and it's in a high state when the balance control task is in the running state. So that's the running state. So I'm going to collapse it and refocus on the region of interest. And here we have the balance control activity, right? Every time the balance control task gets executed, this waveform is going to go high. So it's basically a periodic waveform over time. And I can measure the frequency of this waveform using my measurement tool, right? I can import that waveform, pick all the types, and then I want to measure the frequency, right? So that's pulse train, create a new plot, and just for the visible region of X, I apply it. And here we see that we've generated a new plot which basically measures the frequency of this waveform over time. And you see glitches here and there, which basically is going to be a measure of a jitter in the system, but we'll do that measurement in just a bit. But we see that the frequency is close to 208 Hertz, which is more than what we want, so it's pretty good. And what I'm going to do now is I'm going to try to measure the jitter, which is basically the standard deviation of this waveform. So I'm going to again pull my measurement tool, get my statistical palette, import the waveform. I don't want to fit a baseline in this case, but what I do want to do is measure the mean, median, maximum, and minimum, sure, and then the standard deviation on the visible region of X again. So I apply that, and there we go. So it's 59.911 millihertz. That is the jitter that is the jitter and the frequency at which we are processing the balance control function of the system. So that's like sub 1 Hertz, right? And it's a pretty good number for jitter. And similarly, let's say I want to try to understand the duration of time it takes for me to acquire sensory inputs, take my control action, output the control actuation signal that was computed as the control action, right? So I want to basically measure the duration of time I spend doing mathematical processing and I/O related activities within my balance control task. And I want to see if this duration of time is consistent over runtime, right? So once again, I'm going to select my balance control activity, get my measurement tool, and this time I want to measure the pulse width of that wave train, right? Again, generate a new plot, visible region of X, apply that, and we see that this is how the pulse width of the balance control function changes over time. The y-axis is auto-scaled, but you see that the range is between 246.5 microseconds to 252.5 microseconds. Once again, I can use my measurement tool, get my statistical palette out, import that waveform, and measure the mean, maximum, median, minimum, and standard deviation. There we go. So the standard deviation is 1 microsecond. This tells me that the worst case time period or duration of balance control computation lies well within a time window of 251.47 microseconds plus or minus 1.0335 microseconds, right? That's the jitter of balance control duration. Moving on. Before I wrap up this demonstration, I want to spend a small amount of time discussing some of the other kernel runtime specific agents that are available within the Nucleus palette category. Especially I want to focus on CPU usage and memory usage agents. So we have this agent that basically on the click of a button asks me for the time period over which I would like to average for my CPU utilization calculation. So I've specified that as 10 milliseconds, and I say OK, and it generates a profile of CPU utilization over time. We see that we repeatedly incur 100% usage, and if we see Y back here, we see that the display control task is taken 100% CPU usage, and it's getting preempted by the higher priority balance control task, as you see here, but it's taken 100% CPU usage because the CPU is busy. And if you think about why, because the reason is that the display control task basically updates the LCD display over a UART interface, and the UART driver is a poll driver that we've implemented. So for that reason, we are incurring 100% of CPU bandwidth for the update process. Let's go back here, and so that is the CPU utilization agent. I'm gonna talk real quick about the agents we have under Nucleus memory usage category as well. So let me add the Nucleus memory profile agent. So what this agent gives me is all the memory pools that are present in the system and how the system memory is utilized over time. If I unzoom and expand upon a region where there is some activity, so this is the system memory utilization profile. So you see an increasing profile, and we only have one memory pool that's present in the system memory pool. I mentioned that we've added an external RAM module for purpose of trace data logging. So once that RAM module is initialized in software, we add that memory to the system memory pool. So you see the spike in memory availability, and then we use that memory for trace buffer allocation, and that's why the spike drops down. Basically, I can once again enable my tooltip functionality, hover over any region on this profile, and get a more in-depth understanding of how much memory was allocated, who was the allocator, what was the pool size, what is the available memory, and various other interesting aspects of a particular allocation. I can also right-click here and basically use this option to navigate back to source code and and actually see the point of memory allocation. So if I see an anomaly, I can easily navigate back to source and see who did the memory allocation and whether it is to happen. Come back here. So let's really real quick see the usage of the dynamic memory statistics agent as well. So this is a statistical agent which is going to give you some interesting statistical information about memory usage over time. So click on that. So here is dynamic memory usage in the system. So this gives a nice pie chart of memory used versus memory free. And here we have a list of allocators and the respective sizes, and also it shows which pool memory was allocated from. We have a horizontal bar graph of top 10 memory allocators. This large chunk was allocated for trace data logging in the system. And down here we have a list of leak suspects. This is basically a list of memory that was allocated but not deallocated. So This gives you a very interesting overview of memory usage that's present in your system. And once again, here I can click on any of these entries and navigate back to the source code to the point at which the memory was allocated. This concludes this demonstration. Thank you for your time.